efficiency of perovskite solar cells is 25.2. There are people that already has 25.5, 25.6, very close to silicon, okay? And this is very impressive because Halide perovskites have been able to obtain this efficiency in less than 10 years, right? When for silicon, it has taken more than 30 years to get this efficiency. So we don't think, or I don't think that these two technologies are going to compete. I think they will work in parallel because Halide perovskite can do things that silicon cannot do, and vice versa. Okay. So of course, this is a shift on the mentality of how we fabricate these solar cells. If you work with inorganic solar cells, or for example, silicon solar cells, you're working with high crystalline materials, single crystals, and very high temperatures. And right now, what we are doing is to fabricate in these inks that we can easily be transformed into thin films through printing techniques like roll-to-roll, inject, or screen printing techniques, right? There are also, of course, the cost of fabrication is, of course, very low, and they also have very low carbon footprint, these Halide perovskites. Of course, the technological impact, this is what is going to be in parallel to silicon, is very important because we can make it low weight, different colors, flexible. We can put it on textiles, for example. So we believe that this technology is going to be very important for the future of the Internet of Things, especially because perovskite solar cells have shown to have a very good efficiency and much more stability when you work with them into indoor lighting, for example. So this is something that we are also working in our laboratories of power devices, applying these Halide perovskite solar cells. However, I'm not talking about this today. I'm talking about some of the challenge. As you can see here, there are different challenges. Three of the most important you can see here. The first thing is that even though we have very good efficiencies for these perovskite solar cells, we have to go beyond, we have to get even more efficiency. Why? Because that's the only way we can reduce its cost and compete with this current fuel energy for fossil fuels, right? So one of the many ideas to increase efficiency, since we are arriving to the theoretical limit is around 30% efficiency of these perovskite solar cells, also for silicon solar cells. One of the ideas is to work with tandem devices. Okay, tandem devices can be two perovskites, one perovskite on the other. You can also make it triple. This is the theoretical value that you can get. And because of how cheap it is to fabricate them, there is a lot of possibilities that this will become a huge, very important in the future. There is another challenge that is the toxicity of lead. As you know, this Halide perovskite, the main component is lead. So right now there's a lot of work being done on replacement of this lead for other more or less toxic materials. And for us that we have been working on stability for so many years, the challenge of stability is very important. As you probably know, these Halide perovskite are very sensitive to many ambient conditions like moisture, oxygen, light, temperature, electric field. So all of these are being very, very hard, very strongly studied by the research community in order to increase the stability. Right now, silicon solar cells can offer 20 years stable devices, and we have not been yet. Of course, this technology is more recent, so we don't have that much time to prove it, but I think things are evolving very, very nicely. So we published this paper last year, in case some of you are working on stability of Halide perovskite solar cells, and these are ISO protocols. These protocols are related to how we can characterize these perovskite solar cells in order that we can compare our results with what people is doing in other countries and other laboratories. Okay, so this is very important to read it, to see how the stability test can be performed. If you're interested, you can read this. I will talk about this a little bit more later. So if you analyze in this table, what I put is the different perovskite solar cells that are very stable. Okay, so in this paper that I showed you before, one of the things that we say is that in order to have a stable perovskite solar cell, you have to have a solar cell that can last 1,000 hours under one sun irradiation without losing more than 10% efficiency. Okay, so those solar cells that can maintain more than 90% of their initial efficiency over 1,000 hours under continuous irradiation, some of them, not all of them, are here, are very limited. I mean, you can see that more and more we can see more publications with this type of devices, but there are not that many. And especially if you include temperature and irradiation together, is terrible. There is not many examples that you can find. However, this is only for you to show you that you can find, I mean, we still have to find what is the key to obtain these materials as stable, because, for example, people talk a lot about the instability of spiral. However, you can find in this material, this is, for example, if this is the transparent oxide, this is one transport layer, and this is the opposite transport layer. So you can see that you can have all types of solar cell, normal configuration, inverted, or even carbon-based. These are the most stable solar cells, perovskite solar cells. Or you can find almost any material. You can find a spiral here, okay? And you can find C60, you can find all types of materials. So it's not very clear exactly what is going on in the solar cells and what is affecting the stability of these devices. So one of the things I want to talk to you about today is additive engineering. There are many methods that are being used in order to improve the stability of solar cells. But this additive engineering means that people is adding these additives on the surface at the interfaces with the transport layer, but also inside the solution when you prepare the Halide perovskite. And what you want to do is to passivate defects, because defects are recombination centers, okay? But I just want to show you this example where these two groups, these additives were used in this solar cell. And what we observe here is that it works very nicely, because you can see that an increase in voltage. You can see the values here. This is the different types of Halide perovskite. You see an increase in voltage, and when you increase voltage a little bit, you increase also power conversion efficiency. This is related to non-additive recombination. And what it means that these people is passivating deep defects, okay? So you passivate deep defects, improve efficiency and voltage. But however, we observe that not always you obtain an increase in stability, okay? We have in our mind that as long as you increase efficiency and voltage, you are passivating defects through non-radiative recombination, eliminating this recombination, and then you should have stable solar cells. Usually when you do this, you obtain better stability than the solar cell without the additive, okay? But not always results that you have a very stable device. In here, for example, you can see that in only 25 hours under light irradiation, always talking about under constant irradiation, okay? Yeah, you can see here that only after 25 hours, you already have 30% efficiency loss. So this is not a very stable solar cell. However, the voltage and the efficiency again were very good, okay? So this is another example where this is a very recent one, this is last year, okay? And very, very nice work on the tandem solar cells. And you can also see that in this work, they use different additives, okay? Two-dimensional additives. And you can see that the efficiency, depending on the concentration of the additive, the efficiency increase when you optimize the amount of additive that you use. And for us, it's very good because you increase the power conversion efficiency. And however, when you go to this stability of the device, even though it lasted 1,000 hours, it lost 20% of the initial efficiency. So this is a very stable solar cell, but it's not stable enough to say our devices or the technology is already stable. Okay, so with this idea in mind, I want to show you that, or to tell you that Halide perovskites are not classical semiconductor like silicon or inorganic semiconductors. These are soft mixed ionic electronic conductors. So this soft nature is what makes this Halide perovskite to be able to be processed in a solution processing and to make it on flexible devices. That is very positive for what we want for our technology. However, soft also means weak bonds, okay? And also means that you have, and this ionic electronic conductivity means that you have ionic motion. And this ionic motion what makes Halide perovskite solar cells so stable. So what we have to do, we have to be able to engineer these ions. We have to immobilize these ions and engineer by this additive engineering, right? So these are some examples of the defects that you can find in Halide perovskites. Just for you to see how many you can find, okay? You can have vacancy, you can have interstitial, etc., okay? And you can find in the crystalline and the thin film, multicrystalline structure of the thin film. You can find these defects when you have a line defect, for example. You can have a ground boundary. This is a ground boundary here, okay? And then you can see that the stoichiometry of the Halide perovskite is not what we are looking for, and that's where we have some defects. So I repeat that these defects are recombination centers, and we don't want them there. And there are different types of defects in very general way. Depending on defect formation, you can have shallow defects and you can have deep defects or deep traps, right? In classical semiconductors, shallow defects are negligible. You don't care about them, okay? Because you don't have ionic conductivity, right? So only deep traps are important, and you try to passivate these traps, eliminating this non-radiative recombination. However, in this Halide perovskite, these shallow defects are related to these ionic electronic properties. So the most, you can see here that the formation energy is low for shallow defects and very high for deep traps. So it's very easy to form these shallow defects, this ionic movement. And in reality, these shallow defects are the responsible for phase segregation, ion migration, and also what we know about hysteresis, right? And we want to passivate. This is, I cannot pass. Okay, this is this point effect, just to have an idea about the formation energies. Here you can see some deep point defects that have high formation energy. You can see some examples of these deep trap defects are, for example, under coordinator halides or lead, okay? And also those that are shallow point defects with low formation energy are, for example, iodine or methylammonium, that we all know that they are the most mobile ions in this Halide perovskite, okay? Okay, so additive engineering, what people is doing is there's tons of information about the different additives people is applying right now in order to increase efficiency and stability. These are just some of the examples. And what we did, some other examples, and if you analyze it, there are several reviews, but if you analyze all of these additives, you can see that people uses carboxylic acid groups, they use amino groups, and there are not too many people applying, for example, phosphonate groups, okay? So in our work, okay, I'm sorry, this is again, I'm gonna skip that one. So in our work, what I want to show you today is how we use this 3-phosphonate propionic acid as additive in our solar cells. And I will show you how by passivating shallow defects, we have been able to understand that these shallow defects are the responsible for high stability of this solar cell. You will also see that this molecule is not passivating or not is not passivating deep defects, okay? That means that we are not increasing voltage and we are not increasing efficiency for the as-prepared devices, as you will see right now. But the message that I want to give you today is that you have to be aware that shallow defects are very important because are related to ion migration, okay? And if you use device or additive engineering, you have to think about passivation not only a shallow, not only a deep defect, also on shallow defect, and we have to be able to passivate both. It's not easy task, you will see later, because everything matters, but I hope that you can get this a message from my talk. So what we did, I'm sorry, also, please look at the molecule, and you will see that we are not using amino group, we're using phosphonate, and we are using carboxylate groups, okay? And we believe this effect is made by the phosphonate that you will see in our results. Okay, so let me continue. So what we did, we start working with many very big amount of molecules. Okay, these are just some example, and you can see the red one here is our reference device. This solar cell here doesn't have any additive. Okay. So we were using a lot of these additives with these two functional groups, and you will see that it was very difficult to obtain even the same voltage or efficiency. You can see the efficiency was always very low. So we finally arrived, after a lot of work, we finally arrived to this family of additives with the phosphonate and carboxylic groups. And what we did, we analyzed the family, increasing the chain length of the alkyl group here, okay? So here you can have the reference devices here and chain length increase in this way. And you can see that we were not able to increase efficiency because the voltage was always below or only similar for for this molecule that has 3 carbon groups. So when we choose to work with this molecule that I will call it H3PP. And what we did next, this is the result. What we observed is that we have to optimize the concentration that we use of this additive very, very carefully, because it's not too much amount of the additive that you need. So you can see here, please see here below that the blue one is the reference, okay? And our best one is this one, okay? And you can see that we were unable to improve 4-dimension efficiency, okay? Here's the voltage. Also, the voltage very similar. We have never been able to increase voltage above the one that the reference without the additive. And in this case, we were thinking about, or we don't have any additive here because we are diluting too much, or we are not passivating deep defects, right? Because if we passivate deep defects, we have non-radiative recombination and the efficiency and voltage should be increased. So we are not doing that. That's the first thing that these results told us. So this is our best result. We obtained 21% efficiency for both the reference device without additive and our best solar cells with the additive, okay? Then we also observe, you can see here the voltage again, but you can see we make many analyses to the as prepared devices, as prepared materials, and also the devices, and we observe in every cases. In any case, we always obtain the same properties. Like as prepared materials, they were both the same. With and without the additive, we didn't obtain with the optimized amount. We didn't obtain any improvement. Okay. So in here you can see that charge carrier lifetime related to non-radiative recombination and the density of defects were very similar to both with and without the additive. And then also this technique is optical probe terahertz spectroscopy. Is telling us a little bit about the changes that we observe depending on the light, for example, photoconductivity. And here we also observe that the mobile charges, because of light, are very similar in both devices, with or without the additive. So we were very concerned about this. We also make many other tests to our solar cells, trap density, for example. We want to see the trap density we have in our devices. We make state charge limiting current analysis. We also make line density dependent VOC to see recombination, transient photocurrent, upper circuit voltage. You can see in all results there were very similar results. We were very surprised about this. What happened later is here. This is the most important part, because we analyzed 1,000 hours under one zone in nitrogen, and you can see the orange curves correspond to our solar cells with the additive, and the blue curves corresponded to the solar cells without the additive. And then you can see that you have circular and squares, okay? It means that we have two different types of halide perovskite. It means that it was reproducible if we change the halide perovskite. The only difference is that one has rubidium and the other one, this one with the, let me see, the one with in circle is the cesium methylammonium formaldinium, and the one with the square has rubidium. Okay, so this effect that we observe here is because of we believe it's in the interface with this pyro, and we have some charge accumulation there, okay, because of the rubidium. But in general, what we observe is that at one zone, we observe very, very good stability. You can see that we didn't have any loss at the end of 1,000 hours. I think the worst solar cell had 2% efficiency loss. That's very impressive for a solar cell, okay? So we observe this, and it was reproducible. You can see the error bars, and we say, well, there's something really happening with this additive. It's probably not working with improving the formation efficiency, but it's working with the stability. Then we also make another test. You can see it here. And what we did, we increased the irradiation, okay? If you read this paper, Nature paper that I told you about, I will show you later. We also, I mean, it's clear that if we increase the amount of light irradiation, the degradation of the devices and the material will be even harder, okay? You are really stressing the devices and the materials. In this case, what we observe that even increasing to up to 1,000 sun, 100 sun, we observe that our devices is the orange one with additive show very stable and reproducible results. So it was very interesting to notice, right? So now we have to understand what is really happening, okay? How come we are not improving efficiency and voltage, but we have very good stability? So we try to analyze the material, and we realize that this additive is not getting incorporated into the crystalline structure by telling us by this X-ray diffraction analysis. We also analyzed our nanocrystalline structure, okay? And we observe that we have small grain sizes, as you can see here. And this is very interesting because if you see most of the paper, not everybody, but most of the papers of what we were trying initially, everybody was trying to do initially, is to use to play with these additives in order to increase the crystal size of the halide perovskite. If you increase the crystal size, it means that you are producing very high quality thin films and you have less defects, right? So that's what people were trying to do. In our case, however, our grain sizes were not as high as everybody else was looking at. This is not only typical of us. We observed that since last year, probably, or year after. A lot of people is observing this kind of trend that the grain size is not increasing. Our TEM analysis, what the analysis showed was, and you can see here the reference without additive, and this is the reference with the additive. And you can see very homogeneous thin film with the reference, and you probably know that when you make thin films of this halide perovskite, many times you obtain other or nanoparticles around. In this case, we observe that we have rubidium lead iodide, okay? So the TM analysis showed that it was very homogeneous in film. Then we also analyzed by electron energy loss spectroscopy, just to see where our material is. So our additive has a phosphorus. So you can see where the phosphorus is, and you have an idea if it's only at the interfaces and the ground boundaries, where is it, right? And we observe a very homogeneous distribution of this phosphorus in the whole device, meaning that the additive is very well distributed. The additive is even within this ground boundary that you see here, right? One more thing is also a very nice, the interaction between the additive and the halide perovskite, and one very nice result was the one observed by FTIR. And you can see that the peak of the absorption band that correspond to the phosphonate at 1268 was observed to have some shift to 1243. If we analyze the peak for the carboxylate, we observe no change at all. This is very interesting because it's telling us that it's the phosphonate that the most important, or has the most interesting interaction with the halide perovskite. Okay, one more thing that we did is that we tried to see, okay, this is related. I mean, we know that stability is related to ion migration. So what we did, we made some impedance spectroscopy to analyze if we have some reduction or not of this ion migration when we add the additive. And we effectively observe that if we add this additive, we have this reduction in ion migration. However, impedance spectroscopy is not as good as certain and other techniques. And what we did next also to see ion migration was the use of this activation energy. So we analyzed our material with and without these additives by temperature dependent conductivity in the dark. And we very clearly observed that activation energy for the for our material, it was larger than the reference material without the additive, meaning that ion migration is mitigated. Okay. So then we were not sure what's really happening. I mean, all of this is not direct evidence. So we make also so DFT calculations, and together with the FTIR result, if you remember, with the FTIR, we observe a shift on the phosphonate group, okay? And it was very well correlated with our DFT calculations. And what DFT calculations told us is that it was the interaction, the chemical interaction between the halide perovskite and our additive was through hydrogen bonds. Hydrogen bonds that come from the phosphonate, the formaldinium, and also the iodine. Okay, so it was clear for us with all of these experiments that we are passivating, that we are immobilizing ions. And also, it's also clear that is the phosphonate that is making this effect. It's also clear that we are not passivating deep defects, right? But it means that we are passivating shallow defects. We are not sure. So the next thing we have to do to prove finally there are shallow defects, that the ones that are affecting this result the most. What we did is the analysis by thermal admittance spectroscopy tells us exactly if we are working with deep defect or shallow defect passivation. And you can see here in blue the halide perovskite with no additive, and in orange here the halide perovskite with the additive. And you can clearly see that that when we pass from one to the other, and you can go to this curve here, you can see deep defects here. D2 is deep defects, and D1 is shallow defects. So we have both types of defects with our reference device without additive. Once we add the additive, we see that we don't have any shallow defects here. That means that we are truly passivating shallow defects. This is very interesting because what we are doing now, we finally have been able to separate efficiency and voltage to deep defect passivation and stability through ion mobilization through shallow defect passivation. And I believe we are the first ones to publish this. This has been accepted in June. Probably next week it will be out in case you want to read a little bit about this. So this is what tells us this defect, the no presence of shallow defects in our material with the additive, what tells us finally that what's happening is that we are passivating shallow defects. Now, if you remember all the molecules that we use, it's not easy to say, okay, if you use this molecule, you will be able to obtain this, because we believe there's also effect of size. Okay, you can see here that we did start the calculation of the size and how they interact with the Halide perovskite, and one with the best matching in sizes is this molecule, exactly that the one that we obtained. And you can see that you move a little bit the size. Some of them, for example, these with 6 carbons, completely changes. It's not reproducible, very bad reproducibility, as you can see here. This is telling us that everything matters. Type of molecule, the size of the molecule, the type of functional groups, if it's acceptor, if it's donor, etc. So this is the kind of thing we have to look at. I just want to show you some examples in the literature. Well, this is very nice example. Somebody published it last year. And this is, I mean, our next step is to try to do this stability with the higher temperatures. All our analysis were at room temperature. And are very different techniques. This is a very good example. They only have less than 10% degradation after 1,000 hours and is at 85 degrees, okay? And here they are talking about lead immobilization, okay? This is, they are passivating deep defects here. And of course you observe that efficiency and voltage, I mean, they increase the efficiency when they use these molecules. They increase the efficiency and voltage, of course, but it was very interesting, they increase also the stability, okay? However, these studies, they don't talk about shallow defects yet. So I'm sure they are doing something with the shallow defect, but these people is not, people is not analyzing this yet. So this is another example I want you to see. And this is also very, very nice result. This is 40 degrees, it's not high temperature, but you can also see how they replace. This is probably the first, as far as I know. This is from Professor Yang Group in the United States. He talks about the shallow iodine defects, how they accelerate the degradation of the solar cell. And what they talk about is that they replace iodine with these alternative anions, okay? So doing this, they were able to see, I believe they also, yes, you can see here that the efficiency in these solar cells also improve a little bit, not as much as the others that we observed, but you can see that the voltage increase and also the efficiency. So they are passivating also deep defects, but here you can see the stability of the solar cell after 1,000 hours is only 6% loss. That is also very, very good. Again, I insist that the shape and size and type of functional groups are also important for this stability of solar cells. Okay, and this is my last example. I think is very interesting for you to tell you this message that we also published some article of our opinion about this holistic approach. What we did in our lab is to manipulate only the Halide perovskite thin film. In this work, and they do modules, not only Halide perovskite solar cell on their own. What they did is they passivate many parts of the solar cell. For example, they passivate the perovskite surface with these additives. They also passivate all of this at the same time. They passivate the spiral or gold interface, okay, and they also passivate the Halide perovskite with the thin oxide electron transport layer interface with this additive. Thanks to that, okay, They have been able to obtain very good efficiency of the tandem devices, I'm sorry, the module devices, and see how very good stability they obtain. And they published 2,000 hours under one sun irradiation. This is also room temperature, but you can tell us that it's not an easy task. The message is not an easy task. You have to take into account to passivate not only Halide perovskite, also the interfaces. So I think for me, this is gonna be all. So my message is that we have to passivate. We have to look not only to passivate deep defects to increase efficiency and voltage. We also have to take into account shallow passivation, shallow defect passivation. And we have to keep, even though we are able to increase efficiency and stability, we have to analyze shallow defects to see if we are also passivating our solar cells that way. So and another, I think during my talk, I already told you about other conclusions, like it's very important to select the molecule, the size, the type, the functional group that you use. If you analyze clearly our additive, it has two negative groups, right? So usually what you want to choose is positive and negative, but we don't know, we're playing with that. Okay, so this is my message. I hope you like it. I just want to thank all the people involved in this work, especially Professor Anders Hatfield from EPFL and Professor Michael Gratzel, also Professor Sam Strands, and all the students, Haibin and Shawei, they work very hard on this work. My group, and of course the people behind the money, and of course, thank you very much for your attention. Should I read the questions? I cannot hear anything, Danny. Yeah.
Thank you, Professor. Here somebody want to clarify some doubts. Can you able to see through it in the chat box, or otherwise shall I read it?
I'm sorry, I didn't hear you. You make a question. Can you make a question by the box so I can read them?
Okay, Professor. I can be able to read it.
Because I don't hear very well. I'm sorry.
So,
I can see some questions, right?
Yeah, yes. Shall I read those questions?
Somebody else?
Yes. Somebody has asked, can organic additives sustain the working or device temperature?
This is what we did everything at room temperature because we wanted to compare all these characterization techniques. We did some analysis at higher temperatures and it degraded faster. Okay, so our next step is to do it at 85 degrees. That is the temperature that is required for these ISO protocols and for silicon. Okay.
Okay. Another question.
Yes.
Yes, another question asked by the same person. His name is Shukdev Pandey. He asked that can experiments of 1,000 hours be reduced by studying some initial trend or modeling or DOS simulation, density of states simulation?
For us, the simulation that we use it to know the interaction between the additive and our Halide perovskite. Okay. I would recommend if you want, I mean, you don't need initially to do 1,000 hours, okay? If you have to always compare the reference without additive and with the additive, and you need 10 hours. If these 10 hours, it's good, you can keep going. If not, of course, stop this stability test, right? You don't need 1,000 hours initially. What we did, I mean, you observe, we analyze many additives. Of course, we observe the first hours of all the stability analysis, and we only choose the one that stays the longest, right? And that's the way we observe this result. Okay.
Okay. The another question is maybe additives are leading to grain size reduction.
Yes, I think this is a little bit controversial because many people obtain different things, but we are not the only ones obtaining small grain sizes. What I think is that the interaction with the additive and the Halide perovskite is so well distributed that is, you have microcrystallines, microcrystallines or mini crystalline thin film, okay, and that is preventing the grain sizes to be bigger. Yes.
Thank you, ma'am. And another question is, do tandem and multi-layer devices have lesser solar absorption?
No, in principle, tandem, they have more solar absorption. For example, if you a tandem with a perovskite, one of the perovskite will absorb, for example, 550, and the other one will absorb 650. So you have more absorption in the solar spectrum, right? That's the key for tandem devices. Also, if you use silicon perovskite, silicon absorbs in one range and halide perovskites absorb in the other range. That's why they are very well compatible. And then you use more wavelength of the whole solar spectrum. That's the key in these tandem devices.
Okay, participants, if you have any questions, you please use the option raise hand, that we will allow you to ask the question with the speaker. And two more questions in the chat box, Professor. How does the radiation reach the lower layers?
You, in principle, when you have a solar cell, it should pass the upper layer, should let pass I mean, if you have a tandem device, I guess that's the question. If you have a tandem device, the first layer should let pass, I mean, it will absorb only to half of the spectrum and will pass the other half of the wavelength to the next one. There should not be any problem, okay?
Thank you for the explanation. So like the layers can also absorb as well as pass on some of the radiations to the lower layers, and so all the layers can function. All the layers can partly absorb the sunlight, right?
I'm sorry, again, can you repeat the question?
So you're saying that the upper layers, they absorb as well as let some of the sunlight to pass down to the lower layers. So then in this way, like all the layers can function as absorbents. Right?
Exactly.
Okay, thank you.
When
Thank
you
you, ma'am.
fabricate a tandem device, you engineer the absorption layers to not interrupt to each other, okay? One absorbs one part, the other one absorbs the other part of the spectrum. Yeah.
Professor, there is another question in the chat box. How about the organic light emitting diodes? You have mentioned about.
Well, I am no expert on organic light emitting diodes, but you have to have the opposite, right, of a solar cell, because what we are trying to do is to have an excellent combination of charge in order to give light, right? So you have to engineer, of course, all these layers and try to make it work as soon as possible without losing. When you recombine charge, you can also lose some of this light because of heat. So you also have to engineer that for light emitting diodes, but that's not my expertise.
Okay. Participants, if anybody has any doubts or questions, you may write in the chat box. The same we will be asking with the speaker. Or else, if you want to discuss with the speaker, you can choose the option raise hand. We will give the option to interact with the speaker.
Thank you very much.
Yeah, since there is no questions in the chat box, on behalf of the Chettinad College of Engineering and Technology Management, Principal Madam, Administrative Officer, Head of the Department, and Organizing Committee of this eSTEM21, I thank you very much for your wonderful time and wonderful presentation, Professor Monica, ma'am.
Thank you very much for the invitation.
Thank you.
Thank you very much.
This is your second talk with us. We hope that this will be continued in our in your near future also.
Okay, goodbye. Thank you.
Yeah, thank you so much, Professor. And information to the participants, with this, the third session of today has been over. The next session will be about to start around 3 p.m. We request you to please join in time. Around 2:45, you are requested to join in this Google Zoom meeting. If you are facing any internet issues or connectivity issues, you can get the live broadcasted lecture through our college YouTube channel. And once again, I request you, please join the meeting in proper time. And I request everyone to please fill the feedback link for this session 3. The next session is shortly will be started at 3 p.m. Speaker is Neslina K from Basket University, Turkey. The link already posted in the chat box. Kindly verify it. The same link only. Thank you, participants. After you have filled the feedback link, you can leave the meeting. Please join around 2:45 p.m.